So I think Dhruv and Shreyas, you are joining for the first time, I suppose. So can you just confirm whether you are able to hear me clearly? So are you able to hear me clearly? I think you are able to hear me. So I think we'll get started now. Hopefully more people will join as we go along. So so good evening all. So welcome to the third week's live interaction session for the course of on introduction to mechanical vibration. So in today's session, what I have planned is to uh, cover some problems related to some of the topics that were covered in the third week's lectures. So I'll just so for those of you who do not know me, I'll just start with an introduction about myself. So my name is Parth Joshi. I am a PhD student in the Department of Mechanical Engineering at IIT Bombay, and I am a recipient of the Prime Minister's Research Fellowship. And as a part of this fellowship, I have been given an opportunity uh, to uh, to conduct live sessions for this course on introduction to mechanical vibration. So I welcome all of you, and I hope you find these sessions useful. So the main objective of this session is to help you like understand whatever theory that has been taught in the lectures like in a better way through some of the problems related to the topics that are covered in the lectures. And I am also trying to uh, you know help you to understand some of the concepts better by giving some demos or some activity. So in the last week I had suggested an activity, so I'll be talking about that in some of the future week sessions. So in this week's session I have planned a small demo about which discusses an example related to damped vibrations, uh, and how to use MATLAB to solve such problems, and how you can use it to understand how the systems are behaving in a better way using MATLAB. So we will basically use MATLAB to solve the equations, and then so hi Rupak, so I think you had dropped off. So yeah, basically in today's session I am planning to cover a demo on MATLAB. So in the third week's lectures, some of these topics that have been listed here have been covered, so which includes harmonically excited vibrations, magnification factor, the frequency response curve for harmonic oscillations, then we have the examples related to rotating unbalance, which is of important like significance. It is important in practical scenarios. Then we have excitation of the support, that is also very relevant in many of the practical situations. So we'll see some examples. and also energy input and dissipation by viscous damping. How what is the energy that is dissipated because of damping, and what is the power required to drive a certain system when damping is present. So all these things have been discussed in the lectures. So now, so we'll begin the session. So before we start the planned session for today, so are there any doubts or any questions related to the previous? Yeah, so no problem. So yeah, so are there any questions or any queries related to the this week's lecture content or assignment or anything, or the previous anything, any doubts or anything particular that you wanted to ask? Any questions that you want to ask? Okay, so what is your question, Deepak?
So can I share my screen?
Yeah, sure. I'll just stop sharing my screen. Yes, so go ahead, Rupak. So what did you wanted to discuss in this?
How do you please discuss this?
Sorry. So have you joined from two devices? So if you have joined from two devices, you have to switch off your audio output from one of the devices. Hello, Rupak. Are you able to hear me, or? So what is the question that you have in this? Whatever that you are sharing. So Rupak, can you just tell me what is the doubt that you have in this? Hello. So Rupak, are you still there? So assuming that you are there, and you are able to hear me, I will just maybe tell you what I understood from this problem. So I think you are supposed to find out the natural frequency of vibrations of this ball, whatever ball that they are calling. So this ball is actually pressed into this chamber and then released. So what will happen? So when it is pressed down a little bit, and so then there will be a small change in the pressure, and like so let us say at some position which is shown over here, the mass is in equilibrium. It is it is in equilibrium with whatever pressure. So the pressure inside that air chamber is balancing the weight of the ball, so it's able to float at whatever position that it is shown. So now if we now press it down, what will happen is that the pressure on the bottom of the ball, that will increase slightly. So then there is an unbalanced force, so you have pushed it down, and there is again a restoring force which tries to bring the ball back to its equilibrium position. So the pressure locally has increased near the ball, and so because of the air below the ball, that is slightly compressed, right? So then so there is some work done by pushing the ball down into the air chamber. So let us say there is some small change in the volume dV, and if that increases the pressure by some amount dP, let us say, so then the new pressure will be, let us say, P plus dP, and the change in the volume is, let us say, dV. So the new volume of the system is like V minus dV, let us say. So we are talking about the air which is below the ball inside the chamber. So these are the two changes in the states of the so if you push it down by, let us say, some amount dx, then we will assume that the it's like the work done, like the volume change is like the cross sectional area of the ball into basically the dx. Let us say cross sectional area is A, so A into dx, let us say, is the displacement, like the volume, and that is the volume change because of that. So let us say dV. So then and it is given that the pressure volume variations are isothermal, and so using the ideal gas equation, so you can basically try to find out the relation between the change in pressure and volume. So PV is equal to constant, right? So then when it is isothermal, so the new pressure P plus dP whatever and V minus dV, so you can find out basically the relation between dP and dV using that, and then that you can basically, so we need to find the relation between the force and the displacement. So and then that will result in some acceleration. So that's what the approach is for solving this problem. So Rupak Kumar, so can you hear me, or so I am actually trying to address your question. So I am not able to hear you actually, but I don't know. I mean, so hopefully I have resolved your question. So can you just confirm that? Sure. So can I then? So shall we proceed with whatever session that we have planned? Any other questions? Does
No,
anyone
sir.
have? Yeah, sure. Okay. So have you understood the approach?
Yes, sir.
Okay. Any doubts?
No, sir.
Okay. Thank you. Sure. Then we'll start with our session. So in today's session, I am actually planning to give you a small demo on how you can use MATLAB to solve some of the vibration problems. So as usual, we'll just go through some questions, some conceptual questions, some numerical questions, and then we will then proceed to the demo on how to use MATLAB. So before we begin, so if any one of you are you familiar with MATLAB? So if not, that's okay, we will get to it later. So yeah, so I think we can get started. So in the first question that we have, it is given over here. So it's actually, there is some problem in displaying the question. So I think once I share the PDF of that, so I think it will appear correctly. So basically what the question asks is that in a forced vibration problem, so we have two components like in the overall response. So what is the part which represents the steady state response and what is the part which represents the transient response? That is being asked, and also about the frequency of forced vibration. So the options are like complementary function, particular integral, applied frequency and natural frequency. So you have to select 3 out of these options that will be filling the blanks of the in the thing. So can any of you tell me what is the possible answer over here? Two, okay. So 2 is what? Particular integral. Yeah, so particular integral is what? So the first, you are saying the first fill in the blank is particular integral. Yeah, okay. And then what is the transient response? Complementary function. Okay, fine. And then what will be the frequency of forced vibrations? Will it be the applied frequency or the natural frequency? It will be the applied frequency. So you are right. So when in forced vibrations, so you have basically the steady state response, which is basically the particular integral. So when the transients in the forced vibration they die out, you have basically the particular integral or the particular solution of a differential equation that represents the steady state response, and the complementary function is basically which represents the free vibrations or transient response of the system. So that's the second answer. And then yeah, so eventually when the transients die out, then it will be mainly the vibrations at the frequency of the forcing which will be present in the system. So it will be mainly the vibrations at the applied frequency. That will be the answer for the third part. So just hold on for a moment. It has started raining over here and I think there is some noise in the background. So I'll just hold on for a moment. I'll just close my window. Yeah. So any questions? So the next question is that so in a damped system, so when it is excited by a harmonic force, it has a magnification factor of 5 at the resonance frequency. So from that we have to find out the damping ratio. So now we will first just write what is the equation for the magnification factor, let us say m. So here, this is the expression for the magnification factor. So R is basically omega by omega n, where omega is the applied frequency and omega n is the natural frequency, and zeta is basically the damping ratio, which represents the ratio of the damping present to the critical damping. So now what we have been given is that, so it is at resonance frequency. So here then this will be nearly equal to 1. So the value of R will be nearly equal to 1 at the resonance frequency, right? So then what will be left with? So then the magnification factor will be reduced to or so 1 by 25 is equal to four zeta square. So we will basically get zeta square is equal to 1 by 100, or we will get zeta is equal to 0.1. So is this clear? Okay. So now we'll proceed with this question now. Here, so we have been given a spring mass damper system. The stiffness, the mass, and the damping ratio damping factor have been given, and it has been asked to find out the steady state and total response of the system under this harmonic force that has been given over here, and so the initial conditions have been specified. So now how do we solve such a question? So what will be the approach? Can anyone tell me how will you solve this question? So you can just unmute yourself and speak. So any idea how you will solve this such a question? Complementary function plus particular integral. Yes, right, you are right. So right, so for the complementary function, so what will be your first approach? Like how will you basically characterize this system? Like how first, like how will you then make sure, like how would you determine what is the complementary function? Any guesses? Comparing equation in the sense, f is equal to 200 is basically you mean uh, yeah, w is equal to 10, so that omega, yeah, so the applied frequency is 10, right? And the natural frequency is, it will be, so the natural frequency is, yeah, root k by m. So just a moment, I lost my screen share. So here, so the natural frequency is root k by m, so which is root 4000 by 10, so which is 20 radian per second. And here if we compare the equation, this equation with whatever is given, so we will come to know that omega is 10 radian per second. So if we basically see the what is the frequency ratio, so it is 10 by 20, which is 0.5. So it is half of the natural frequency. Now how do we find out what is the nature of the damping? So for that we need to find out what is the critical damping. So the critical damping is given by 2 root k into m, which is 2 into square root of 400 into 10. So what is the value of the critical damping here? So it's, sorry, it should be 4000 into 10. So it's basically 2 into 20 into 10 or 400 Newton second per meter. So that's the critical damping. So here, so what is the damping ratio of the system here? So it is C by Cc, or it is 40 by 400, which is equal to 0.1. So basically since zeta is less than 1, so it means that the system is under damped. Right, so the system is under damped. So now since we know that the system is under damped, we know what is the general nature of uh, the free vibrations of the system. And now uh, what about the particular integral or the steady state response? So for that we will consider we will have to consider basically a particular solution which is of the form which is shown over here. So you must have already studied these things in the lectures. So how do we derive the response to the force, like forced vibration? So for the forcing, we, let us say we substitute, like we assume that the force is of some, like f naught e to the power I j omega t of that form, and then let us say the steady state response is of the form, let us say x is equal to it is of the form x e to the power j omega t. Then we substitute it in the differential equation, and then we basically find out that the steady state amplitude is given by this equation. So this is basically the steady state amplitude, and this is the phase difference for the steady state vibrations. So now we know basically the form of the particular solution, and now since we know that the system is under damped, we also know the general form of the solution for for an under damped system. So basically this is the free vibration of the under damped system. So the expression which is given over here, so this is basically the total response. So this part is basically the transient, and this part is basically the steady state. So for this we basically will use the information that has been given to find out the total response. So since we derived that zeta is 0.1, we know the natural frequency, so we can basically derive the damped natural frequency. So it will be root of 1 minus 0.1 square into omega n, which is so omega d is 20 into root of 0.999, right? Right. So you can find out the exact value of the damped natural frequency. Now so for finding out the total response, so what is known to us is that we can find out basically the value of the phase difference phi, because it depends on the basically the damping and the applied frequency, the mass and stiffness properties. So this is known, and we know omega. We also, and then we can also calculate the value of x from these. So basically the values of x and phi are known to us. So we can calculate x. So So here f naught is, it was yeah, so f naught is 200. So and it's basically the omega is 10 radian per second. Yeah. So yeah. So so since f naught is 200, so we can basically calculate x is f naught, which is 200 upon root of k minus k, which is basically 4000, minus mass, which is 10, into omega, which is again 10 square, the whole square, plus damping, the damping value, which is c, into omega, which is 10 whole square. So using this expression, we basically we can calculate the steady state amplitude. So what will be the value of the steady state amplitude approximately? Can anyone tell me? So it will be basically 200 on root of 2000 square plus 400 square, which is 200 on okay 0.493. Okay, so let me check. So I actually got about 0.06. So can you just check your calculations once again? So I think you should get something about 0.06 or so. So anyway, so yeah, we have found out x, and similarly we can find out phi, which is tan inverse c into omega, which is 40, into omega, which is 10, upon k, which is 4000, minus 10 into omega square, which is 100. So we can also find out basically the value of phi using this approach. And so we got the value of x and phi. Now our job is to find out the value of x naught and phi naught in the total response, so which will be determined from the initial conditions. So So we know x of t, so basically we will determine x naught and phi naught from the initial conditions. So we will basically substitute x of 0, which is x naught. So we will put time t is equal to 0 and then apply basically the value of initial condition, and x dot 0 is basically v naught, whatever that has been given. So we will basically find out in the total response, we will find out the expression for the value of xt basically in terms of x naught and phi naught. Then we will have to differentiate the expression for x of t. So x dot t, so it will be basically given by d by dt of x cos omega t minus phi plus, so into, let us say, x naught cos omega dt minus phi naught. So we have to differentiate this to find out x dot t. So it will be minus omega x sine omega t minus phi plus, so now here we have two functions, so it will be x naught into minus zeta omega n into e raised to minus zeta omega n t into cos omega dt minus phi naught plus x naught into e to the power minus zeta omega n t into minus omega d sine omega dt minus phi naught. So we got the value of x dot. So what will be x dot of 0? So it will be minus omega x sine minus phi plus minus zeta omega n x naught and into cos phi naught. So cos of minus phi naught will be cos of phi naught, because cos is an even function, plus x naught into minus omega d into sine minus phi naught, so which will be same as minus sine phi naught. So here it will be minus minus, so it will be become plus, so something like this. So we will get the expression for x dot of 0, and we also know x of 0. So x of 0 will be x cos phi plus x naught cos phi naught. So we know x and we know phi, and so we have to find out x naught and phi naught. So we have two equations in two variables, so we can solve these two equations to get the value of x naught and phi naught. So for the free vibrations, alternatively you can also substitute for the complementary function. So you can also substitute it as, so instead of this x naught cos omega t minus phi naught, you can also substitute it as a cos omega dt plus b sin omega d t into e to the power minus zeta omega n t. So this will also, it's also same. So we can, instead of using, so here we'll have the two variables as a and b. So now so I'll just show you how this is solved using MATLAB. So before that, so basically now to get the total response, we need to find the values of a and b, or x0 and phi naught, whichever way that you do. And then so using the information that we get, so we will basically get the value of a and b, and then so we will use that to plot the response of the system. So now what I will do is, so I will just quickly show you how to basically solve these equations in MATLAB, and then use MATLAB to plot how the response will look like. So till this point, anyone has any questions? Okay, sure. So then we will just quickly go to MATLAB. So just, can you just confirm whether you are able to see my screen? Okay, fine. So so now what I have done is, basically I have written a small MATLAB code to solve this problem. So so here in this we have basically in MATLAB we can write small programs to do any mathematical calculations, and then we can use MATLAB to solve different kinds of equations, either linear equations, differential equations, and any sorts of mathematical calculations. So here what I have done is, I have written small MATLAB code to solve this problem. And here in this basically you can write a program, basically so like the way we do any mathematical calculations. So the MATLAB programming language is quite user friendly, and it doesn't have any complicated syntax. It's yeah, I will share this code at the end. So even if you don't have an active MATLAB license, you can still use this code in another open source software called Octave. So you can also, like, the syntax for Octave and MATLAB are very similar, so you can also use this code. Most likely it will run as it is, or you might have to do some small changes. And so here what this code does is, it basically tries to solve for what is the response of the total response. It basically here it's written like the steady state response and the transient response is determined, and then it is basically plotting the response of the system with respect to time. So first, in the first line I'll just quickly explain you the code. So the first line is basically about the time interval for which we are doing the calculations. Then this is the input data, the mass, stiffness, damping, and then we are calculating what is the critical damping. Then the amplitude of the forcing and the forcing frequency have been given, and then we are writing down our initial conditions, and then we are basically calculating the natural frequency and the damping ratio from the given data. We are also calculating the frequency ratio here. And now, as I told, like, we are using the same equations for the steady state response in terms of the forcing frequency ratio and the amount of damping that is present. So here, as we calculated, the damping ratio works out to be 0.1, and we have also calculated the phase difference. Now comes the transient response part. So here the code first checks whether the system is under damped, critically damped, or over damped based on the damping ratio. Or here I am directly comparing the damping factor itself. So if the value of C, the critical, is less than the critical damping, then it is under damped. Or you can alternatively write like the damping ratio is less than 1. If the value of damping ratio is 1 or the damping value is equal to the critical damping, then it is critically damped. Then we have the response which is slightly different from the earlier one. So it will not involve any oscillations. The free vibrations part will not have any oscillations, and the over damped part, again its response will be again different. So you would have studied that how the, so it will have, so the characteristic equation will have two real roots if it is over damped. For critically damped, the characteristic equation of the differential equation, it will have two equal roots, and under damped it will have two imaginary roots. So depending on that, the response of the system will be changing. So now what I am doing now is, so I will just run this code as it is with the given data, and now this plot has appeared on the screen. So which shows that how the response will be for the, when the damping ratio is equal to 0.1. So if we observe the response, so up to so on the x-axis it is time, and on the y-axis it is basically displacement. And then so as we move ahead in time, the transient part of the vibrations will die out. So as we see, we can see that in up to about 0.5 seconds or so, the transient vibrations have gone down, and then after 1 second or 1 or 2 seconds, it's mainly the forcing frequency that is being, basically that is the part of the major part of the response, so which is basically the steady state. So at steady state, so around 3 or 4 seconds it has actually reached the full steady state, and like beyond 4 seconds or so, it will be mainly the forced vibrations that will be the steady state response. So that will be the major component of the vibrations. Now you can use this code, so you can manipulate the value of the damping ratio. So if you just here, if you just increase the value of C, let us say now if I make it, instead of 40 I make it 100, so it will change the damping ratio, and now it has changed the response. So the damping ratio is now 0.25. so damping has increased. So if you compare the earlier figure and this figure, you can see the difference. So now the transients die out faster than the earlier case. So likewise we can increase the damping and see how the system behavior will change. So now if we will now just make it to a critical damping value. So the critical damping value was 400. So now we will see how the response becomes when it is critically damped. So here in critically damped system, so there will be no oscillation for in the free vibrations part. So rapidly the amplitude goes down, and then like beyond 1 second or so, the system has settled to its steady state, and then it just keeps oscillating as per the forcing frequency. Now if we increase the damping value further, now if we just make it 800, so then that will make the damping ratio as 2. So now you can see how the response has changed now. So the amplitude has rapidly gone down, and now it like after 1 second or so, it just continues its oscillation based on the forcing frequency. So this is how you can actually just try to use this code and observe what is the behavior. So one more observation that you can make is that, so if you if you compare the amplitude, so the amplitude of the oscillations, like here if we just compare like between damping ratio 0.1 and 2, if we compare the amount of the amplitude of the steady state oscillations, so basically the uh, distance between the this and this, so this if you can see my cursor, uh, so the amplitude of the steady state oscillations has also gone down, and then that is basically what we would expect as we go on increasing the damping. So the steady state vibrations amplitude would actually go down as we increase the damping. So that's what we can see over here. We can basically our observations match whatever the theory predicts. So this is how you can use this code. So depending on what is the value of C that you or the damping value that you put over here, that will change the behavior of the system. Now if we can also try to change the forcing frequency. So our natural frequency is 20. So now if we just put the forcing frequency as 20, which is close to the resonance frequency, then we can see how the, so now because the system is over damped, its resonance effect will also not be so prominent because of the damping present in the system. The system will hardly move now. But if we now go back to our original value of damping, which is 40, we will move to our earlier underdamped system. So now we can see that with time the amplitude is growing, and it is growing to a higher value than the original value of 0.1. So with resonance, more and more energy is being added into the system. Yeah, so Rupak, what was the question? Can you just so I cannot see the chat because I am sharing the screen. So can you just unmute yourself and speak? What was the question that you posted?
Yes, sir. If damping ratio is 0 and ratio of omega and omega n is equal to 1, then
Okay.
what will be the graph?
Okay. Yeah. So then it will be basically it will not be able to calculate here, because see the amplitude will become infinite, and so then I think there is in this code, I think you won't be able to do that. So because the amplitude will come out to be infinite, right? So then you won't be able to. So if I can just make it very small. So I'll just make it very very small, so the damping value, so that you can at least see something. See, so here you can see that the amplitude is growing very fast, right?
Yes, sir.
So that will be the case in case of that. So does that help? So theoretically the amplitude will become infinite when your damping ratio is 0. Yeah, so this is how you can basically use this code, this kind. So you can also create your own code. So I'll share this code at the end of this session. uh, yeah, so any questions? Okay, fine. So then we'll move on to another question which I had. So this was the demo for MATLAB. So So I have another small question which is interesting. So I had a question on rotating unbalance as well as on the base excitation. So because now actually the time is short, so I will just quickly cover this question on rotating balance unbalance, and then we will just quickly also go through the question on uh, basically the base excitation. So I think I will not be able to solve the problem fully, but we will just discuss the approach how to solve such questions. So yeah, so it has been given that we have some machine. Let us say this box is representing the machine. So yeah, so let us say this box represents the machine M, and so it is supported on some spring, and let us say there is some damper, and there is some spring, and this is let us say the foundation of the machine, and it has been given that the machine has a rotating imbalance and its rotating speed has been given. So it has been asked what is the dynamic amplitude of the machine. So the rotating unbalance will be some small eccentric mass, let us say, which is small m, and into eccentricity e. So that has been given as 25 kg centimeter, which is 25 by 100 kg meters, which is 0.25 kg meter. And we know the frequency of which is omega, which is given as 1200 rpm. So 1200 into 2 pi by 60 radians per second. So and we now we have to find out what is the steady state amplitude. It has been given that when the machine is supported on the spring, its static deflection is 0.5 centimeters, or so from this information we basically find out so 445 kg is the weight. So m into g, basically the weight is basically uh, the weight that is supported by the spring. So let us say delta s is basically the static deflection. So the static deflection is given, so we will use it to find out the stiffness of the spring. So m into g is basically the k into delta. So k into, so it is 0.5 centimeters, so 0.005 meters. So from this we will be able to find out the value of k. So we know that what is the value of k. So and then the next step is finding the amplitude of the machine. So for that, what will be the force acting the force acting on the system. So let us say this, there are some rollers and the mass is, let us say, constrained to move only up and down. So the forcing that is acting on the system, that will be of the form me omega square. So it will have a horizontal and vertical component. So the horizontal components are balanced by the wall reactions, and the vertical component is the one which is basically me omega square into sine omega t, which will be contributing to the forcing. So we know that for any general forcing with f naught cos omega t or sin omega t, what will be the nature of the force vibration. So we will use the same approach over here, and so we will use the same, like mx double dot plus the same differential equation will be applicable here. So here we basically then find out, like we assume that the amplitude is of this form, and then and the forcing is of this form, f naught e to the power j omega t, and then substitute in the differential equation, and then we found out that the value of x is basically f naught upon root of k minus m omega m into omega square whole square plus c omega whole square. So here f naught will be basically replaced by m small m, and here we have basically capital M. So this is basically the equation for the steady state amplitude. So we know the value of k, capital M, we know the value of omega, we know the eccentric mass, and from this we can basically calculate the what is the rotating unbalance. Any doubts? So I will not solve the problem further, you can actually try it on your own. So I will discuss another problem which is so basically after reaching this expression, so you can actually just substitute the values of k and then find out what is the steady state amplitude. So I think you should get you should be able to get the values of the steady state amplitude using that. So I had another more interesting question which is I have shown over here. So generally it's an interesting problem how to basically, so when a car goes through a bumpy road, so it is being subjected to some kind of a forced vibration, and so how do we basically see how the response of the car is when it is subjected to some road bumps. So that is a very critical thing that is to be designed by, so in while designing any car suspension, so we have to ensure that passenger comfort is not being compromised. So for that, we basically have to make sure that the the amount of the extent to which the the car is oscillating up and down when it goes over a bump, that should be as small as possible. And at the same time, we also have to ensure adequate stability and adequate comfort. uh, so there are some design trade-offs involved when we are designing for stability and uh, also for passenger comfort. So when we are trying to ensure passenger comfort, we try to ensure that, let us say, the force transmitted to the passenger cabin is small as possible, or the amount of displacement or the up and down motion because of the car going over the bump, that is as small as possible. So these are the kind of design problems that one would encounter in automobile industry. So this question basically deals with that. So let us say if we model a car which is going over a bumpy road. So here, for simplicity, we will just assume that the road profile is actually sinusoidal, for simplicity. So it is like the road profile is something like a sine wave. And so it has been given that the road elevation varies sinusoidally, and its distance from peak to trough, basically, which is this distance. So that is given as 0.2. So and we also know the distance from between the peaks, so that is also given. So this is given as 35. So we know the natural frequency of vibration, so it is 2 Hertz, and we also know the damping ratio of the shock absorbers. Now we have to determine what would be the amplitude of the vibration of the car. So here we are just considering up and down motion. So let us say if we model the car like this as a block of mass m, and this is, let us say, the stiffness of the suspension and the damping. So we have a spring mass damper system, and let us say we represent this small v. So this wheel is going over the road profile, whatever it is something. So let us say this displacement of the wheel, we call it as y, and we call the displacement of the passenger cabin or car, basically the car body, as x. So we have been given the motion y, and we have to find out the motion x. So how do we solve such a problem? So our task is to basically represent the motion y as a function of time. So how will we do that? So for that, we have to carefully look at what information has been given about the road. So here we know the road profile, so it is sinusoidal. So let us say we call it as y naught cos omega t. So we know y naught. So y naught is given over here. So we know that the distance between peak and trough is 0.2. so y naught will be half of that, so it will be 0.1. And now our next job is to find out what is the frequency of omega. So we know what is the vehicle speed v. So the vehicle speed is, let us say, 60 kilometers per hour. And so we know what is the time required to travel the distance of 35 meter, which is basically the distance between the peaks. So that will correspond to the time period. So here let us say we imagine that the road, like the car is going over the road. So now with respect to a person sitting in the car, it's like the road is moving in the opposite direction with that same speed like as the vehicle speed. So the time period associated with this will be basically the time period t will be, which is distance, basically 35 meters, or let us say we call this as capital L. So then it will be this distance upon speed, so in appropriate units. And so how we find omega? So omega is basically 2 pi upon time period. So then omega is basically 2 pi into p by L. So we basically, in terms of vehicle speed and distance between the two peaks on the road, so we from on basis of that we basically calculate the value of the forcing frequency. Any doubt up to this point? Okay. So now we know that basically y is y naught cos omega t, and we have to find out x. So we will draw the free body diagram of this system. So let us say this is the spring force and this is the force due to the damper. So how do we basically calculate now the spring force? So now the two springs, ends of the spring, so one end of the spring is attached to the car body and the other end is attached to the wheel. So the car is moving up and down as per the coordinate x. So x is the, and here the other end is basically moving as per this. Similarly for the damper, so now for the damper we are concerned with the velocity. So it is moving at, one end is moving at x dot of t and the other end is moving at y dot of t. So that will basically be for the damper C and spring K. So now how do we write the spring force and value of y? So here let us assume that xt is with respect to the equilibrium position, or So we will assume that x of t is measured with respect to the equilibrium position of the car body. So then what will happen then? The basically the that will cancel out the weight, the basically the static deflection due to the spring. So the static deflection part of the spring force and weight, that will be balanced. So then whatever is the displacement with respect to the equilibrium position, that is because of the dynamic force of the spring, dynamics part of the spring force and the damper force. So then the spring force, how will we write the spring force? It will be basically K into x minus y. So because it is pulling downwards, so we will assume that x is, let us say, greater than y for the instant that is being shown, and for the damper we will basically, it is proportional to the relative velocity. So it is basically c into x dot minus y dot. So just hold on for a moment. Thank you. Okay, thank you. हेलो, इसके ऐसे अच्छा, थैंक यू. Yeah, sorry for the interruption. So the spring and damper force can be written in this way. So yeah, any doubts on this? So basically we get the spring force and damper force. So we will now write the equation of motion. So the acceleration, mass into acceleration. So that is basically minus of Fs and minus of Fd, because it is down. So let us say upward, we have upward is positive, and so then it will be minus of Fs and minus Fd. So then we will simplify the equation of motion further. So basically k into x minus y plus c into x dot minus y dot will be 0. So that is the equation of motion for the system. So basically we have our standard, basically with respect to with respect to x, so we have like mx double dot plus cx dot plus kx is equal to kx plus k into y plus c into y dot. So basically now our forcing function is basically k into y plus c into y dot. So in terms of y is y naught cos omega t, so we have the forcing function as mx double dot plus cx dot plus kx is equal to k into y naught cos omega t plus c into y dot. So c into y dot is basically minus c into y naught omega sine omega t. So this is our equation of motion, and now we use the same approach. Let us say we as we apply in other force vibration problems. So we apply like the relation like f is of the form f naught e to the power j omega t. So similarly we apply here y is y naught e to the power j omega t, and then we also apply that x is some capital X naught e to the power j omega t, and we substitute this in the equation of motion, and then we will get basically the expression for x and y. So basically k minus m omega square plus j omega c into x naught, let us say, or x basically is equal to k plus j omega c into y. So if we want to find out the absolute value of the amplitude, so we basically take the absolute value of the ratio of x by y. So that is what will be magnitude of these complex numbers. So it will be k square plus omega square c square upon k minus m omega square whole square plus omega square c square. So here I am skipping some steps, but this is the value of x by y that we will get. So basically this gives us the relation between the amplitude of the disturbance, which is basically y. So this is the road elevation, and x is basically our response of the car or whatever. So yeah, if we try to plot this ratio of x by y, so this is what we would get. So let us, if we try to enlarge this figure, so this is the kind of response that we would get. So when the road profile is such that its frequency matches with the natural frequency of the car body, so then it will be again resonance, cause resonance, and then that will cause high values of displacement transmissibility, or basically the value of x will be very high, or the displacement of the car body will be very high. So that will cause discomfort to the passengers. So that has to be avoided or reduced as much as possible. So we generally try to design the natural frequency of the car body, or basically select the stiffness of the spring suspension in such a way that this displacement transmissibility is as small as possible. So that is the concept over here. So here we have been given the values of k, omega and c. So omega has been calculated, and then we will basically get the value of x by y over here, or the displacement that transmissibility over here. And now the second part of the question is that if the speed of the automobile is varied, we have to find out the most unfavorable speed for the passengers. So that will be basically the so when so when omega is nearly equal to omega n, so that will cause x by y will be very high. So then that will be the most unfavorable speed will be when omega is nearly equal to omega n. So our omega value was 2 pi v upon L, which is omega n, and so corresponding to that we can find out basically the so that will be the most unfavorable vehicle speed. So we should so that will cause so when the vehicle reaches the speed, it will cause very high oscillations of the car body, and that will be so we can actually
এসি যোনটো বুলি কয় যে
hello
এসি মানে কি
yes
এসি মানে ইনচার্জ তো
hello someone actually joined and was trying to speak, I don't know. So I hope this is making sense. So we can try to calculate that. So here we know the value of L is 35 meters, then we know the natural frequency. So the natural frequency is given as 2 hertz. So it will be 2 pi into 2 divided by 2 pi. So it will be 70 meter per second, or it will be so this is actually very high. So this generally any vehicle will be in India, it will be very difficult to achieve such a high speed. So it will be 70 into 3.6. So in terms of kilometers per hour, so it will be more than so it will be about 252 kilometers per hour. So generally we will not be traveling at such high speeds in India, but yeah, so this is one theoretically this is one speed which should be avoided for such a road profile, so that will cause resonance. So this was it from my end for today. So there are some more questions. So there is another interesting question which I have. So but you can actually try it on your own. So here it basically shows that in an aircraft we have an engine, and the engine has a rotor has a unbalanced mass. So now it asks about the what will be the maximum deflection of the engine when it is rotating at some rpm. So here we have to basically model our aircraft wing as a cantilever beam, and the engine is subjected to some rotating unbalance, and that will basically represent some time varying periodic force, so which is some me omega square into, let us say, cos or sin omega t, whatever, let us say sin omega t. Let us say this is acting at some distance small l, and capital L, let us say, is the length of the cantilever beam. So here we have to find out the maximum deflection of the engine at a speed of n rpm. So the omega will be corresponding to the rpm. So omega is n into 2 pi by 60, and the eccentricity and the mass, eccentric mass magnitude have been given, and we have been given that the damping and the effect of the wing between the engine and that has to be assumed to be negligible. So it's like basically a time varying force is applied to a cantilever beam, and then we have to find out what is the maximum deflection of the engine. So we will just calculate what is the stiffness of the beam in terms, so the deflection due to some force applied at this point, and so the deflection at that point, that can be calculated from the beam theory, and that can be basically used to derive the stiffness of the system, and so that can be basically used to get the natural frequency, the frequency of the like the natural frequency, and so based on that we can determine the maximum deflection based on the steady state response to the forced vibrations. So that was it from my end. So that's all from my side. So any questions?
Sir, can you please share the email ID so that I can get MATLAB code?
Yeah, okay, sure. So you can just email me on this email ID. So you can, I'll share my MATLAB code over there. So I have sent you my email ID over the chat. Anything else? So I think then we can end this session. So thank you very much for attending. So we can end this session for today. Thanks.